Welcome back to another exciting episode of Physics with Dr. Von Moss. Today we're talking about angular momentum of linear motion. So what I mean is everything has angular momentum. If it has linear momentum, you can say it has angular momentum as well. It's a little bit we need to talk about how we need to consider how we need to calculate angular momentum, right? And it's relative to what you're talking about. I'm not just going to say that a car driving down the road has angular momentum because there's probably not going to be any rotation in the near future. But I might say that like this situation where I have an arrow, I'm shooting it at a target. Beautiful. But like, let's say say you're in space, right? So things are free to rotate. You don't have to worry about gravity. You don't have to worry about friction. You shoot at a target, but you're a bad shot. So there's your beautiful, beautiful target. Let's make the center of that target red. Gorgeous. Okay. So the arrow has some angular momentum, or some momentum, right? So it's going to have some mass and some velocity it's coming at this with. And it's going to hit some distance from the center, right? So the momentum of the arrow we can find by doing mass times velocity, right? Where the arrow's velocity vector is that way. Now the angular momentum of the arrow, we're going to consider relative to, it has to be measured relative to something, right? So what's going to happen in this scenario? Well, we're in space, it's floating, there's no supports on this target, so the arrow is going to hit the target, and then they're both going to move this way, but while they're moving that way, because it's hitting off center, the target's going to spin, so it's going to kind of do a path kind of like that. So you're going to have linear motion of it moving to the side, but angular motion as well. Well, if it's spinning, it's going to have some angular velocity, right? And that means it's going to have some angular momentum because we can find angular momentum like this. So if we have the basic idea that angular momentum is conserved, that means it cannot be created nor destroyed. It cannot come from nowhere. It has to come from somewhere. Let's underline that. Ooh. Cannot be created nor destroyed. Okay, so where did the angular momentum come from? If in my final scenario I now have a target. That one's actually better, I think. With an arrow poking out of it. That's tear marks in the. Because I'm doing good art, okay? Leave me alone. There we go. And so this thing has angular velocity in this direction, and it's also got linear velocity this way, right? So where did the angular momentum come from? Well, if the target was at rest originally, then that means that the arrow must have had angular momentum. So the way we're going to model that is we're going to say the angular momentum of the arrow is equal to the cross product of how far away it is from the point of rotation and its linear momentum. So let's write that out. distance from point of rotation, cross product with linear momentum. That mostly fits. There we go. Okay, so let's assign some numbers to this problem that we're doing and go ahead and figure this out. So when the arrow is going to have, let's say this R here equals, I mean, targets are pretty big, so let's say 20 centimeters. And let's say the arrow has a mass of 100 grams. And it is fired with a velocity of 50 meters per second. That sounds about right for an arrow. I don't actually know, though. Oh, I'm getting off the page. There we go. And let's talk about the target now. So let's say the target has a mass. So let's put arrow under all of these. So the mass of target will be, let's say it's 500 grams. So half a kilogram. It's initially at rest. And so let's say its moment of inertia then is, well, this is kind of an irregular shape, because if we think about it, we're looking at it from its side, because where is it spinning about? It's spinning about, it's an axis going this way. So if it's positioned like this and the arrow hits it here, it's going to rotate like this. So it's spinning about that axis, but it's the target originally this way, so it's spinning like that. Do I have anything that would be better to show you with? I mean, this is thicker, but this is my wife's thread. So if it gets hit here, it's spinning along this axis. So we have to consider that it's not going to act quite like a stick, but it's not going to act like a disc either, because the disc moment of inertia would be, if it spins this way, would be what we usually use for a disc. So let's just pick a number, because it doesn't have to be accurate, because this is just for learning purposes, and we're not finding moments of inertia. So let's say it's going to be mtr squared. Now what's r? Well, r is going to be the radius of the whole thing. So we have to define that guy too. So r, let's say, is 0.3, just estimating off my drawing, meters. Okay. So there's one other thing I need to consider too, and that's, well, when I do this problem, we'll conserve angular momentum, right? So we're going to get angular momentum initial is equal to angular momentum final. So the angular momentum initial is going to be the angular momentum of the arrow only. So we're going to say R cross P, and that's equal to I omega, right? Now, what is this I that we're dealing with? Well, this I isn't just the target, because the arrow is going to be rotating too. So I have to actually do both. So this actually needs to be I target plus I arrow times omega. So we have to pick what moment of inertia to give to our arrow. So let's pretend that our arrow can be treated like a point mass, just as a simplification. So the moment of inertia for our arrow would then need to be m arrow times the distance from the point of rotation squared. So now finally, I have an equation that's actually kind of useful. So I've got R, which is the number I know, cross mv, because that's the linear momentum, is equal to the moment of inertia of the target, 1/6, mass target, radius of target squared, plus mass arrow, distance of arrow from the center of rotation, squared, times omega. And so now we just need to put numbers in and solve for that omega. So let's do that real quick. So this R we said was 0.2 times mass is 0.1. Velocity is 50. So then I have 1/6 times mass of the target, we said was 0.5. Radius of the target is 0.3. We have to square that. Plus mass of the arrow is 0.1. Distance of arrow from the center of mass is 0.2. And we have to square that guy. Times omega. Ooh, can't see quite all of that. There, we're in good shape. So I'm going to put that in my calculator real quick. I don't know if you guys want to see that or not, but I'm going to put it under here, and you guys can pay attention if you want to, or you can just skip ahead. So 0.2 times 0.1 times 50 is 1. And that's going to be in parentheses. Well, yeah, so let's just go ahead and do this side, then I'll divide. Actually, let's just do it all one time. So I'm going to do 1 divided by, and I want a parentheses. Parentheses. 1 over 6 times 0.5 times 0.3 squared plus 0.1 times 0.2 squared. Close that parentheses. Push equals. So it's going to be, I think it was 0.075 omega. So omega then is equal to 1 over 0.075 or 133.3 radians per second. So that's not all we can do with this problem. There's one other thing we can do with this problem, is we can ask what is the linear momentum of the two, and that's just going to be how we did it always before. But let's go ahead and do that anyways, just for review. And it's good practice. The questions you actually get will probably look more like that anyways. So you want to conserve your linear momentum. Momentum initial is equal to momentum final. So I want momentum of my arrow, velocity of my arrow, plus momentum of arrow, mass of arrow. Mass of target, velocity of target, which this is 0 because the initial velocity of the target is 0, is equal to, now it's definitely an inelastic collision because you're going to hit and stick together, right? So I can just do straight adding them. So I can do sum of the masses, ma plus mt times velocity. Now we're looking for velocity, so we're going to divide and say velocity equals, on this side, right? ma over ma plus mt times velocity a. Put that back into the trusty phone calculator. All right, so I have, let's move that so I can actually see my numbers. Mass of the arrow is 0.1 divided by parentheses 0.1 plus 0.5 close parentheses equals times velocity of the arrow is 50, 8.33 meters per second. All right, so those are our answers. We have, it's going to be spinning very fast, and it is going to be moving pretty fast after the collision. So perhaps if you're actually doing this, you know, you're going to be a outer space archer, you should get a heavier target. Just advice for the future, guys. I think I'm going to call that a video, and I'll see you guys in the next one.